In the previous video, I talked about the issue that we have if we want to calculate the force on a circular cylinder using a potential fluid theory. And well, basically the issue is we get zero resistance. If there's a fluid flow, uniform flow, and a cylinder, potential fluid theory gives us zero lift. Well, that's good. That's expected because cylinder is symmetric, but also zero drag. That was called for a long time, a couple of centuries, D'Alembert paradox. And people didn't know what they need to do. I mean, how to describe the fluid. It looks like everything mathematically is beautiful and consistent, but then at the end we get zero net drag force. And in 1904, it was Prandtl who explained basically what is missing. And what is missing is the effect of viscosity. And the effect of viscosity in particular enters the problem by the so-called no-slip boundary condition, right? So far in D'Alembert or potential flow solution, we let fluid particles to slip along the wall, all right? And then Prandtl said, well, no, fluid particles cannot slip along the wall. They have to stick to the wall. That's the property of the fluid. I mean, he just explained how the nature works, right? He didn't say that I have a new idea. He just said, well, if you look closely to the fluid particles close to the boundary, you're going to see that they're not moving. They're slipping very little in such a way that we can just assume there's a no slip boundary condition on the wall. So this causes friction. So that's exactly like dry friction. It's not dry friction, but it likes dry friction. If fluid particles cannot move, they kind of slow down the flow. And then he also observed another very interesting thing that today we call it separation, and that fluid particles kind of cannot go along the boundary of the cylinder forever, and under certain conditions, at some point they kind of separate from the surface, right? There's not going to be a vacuum. There are other fluid particles that come and fill the space, but we're going to see this little pattern here that we call it separation. And there's going to be vortices here, and again, vortices on the other side. And that also contributes to the drag. Now, the drag due to friction on the wall is called the skin friction drag. And then the drag due to the separation is called form drag, because that drag is a function of the form, the shape of the object, right? So specifically in the old days, if well, probably you've seen the pictures, right? The cars were like this, right? Very sharp corners, like a boxy shape. And these are awful shapes from aerodynamic perspective, because that enhances the separation. There's going to be separation here, right? And vortices, and the separation here and vortices, and separation wherever we have, then we have a huge increase in the drag. That's why today's car are more like aerodynamic, like this, right? No sharp corners, very nice curved shape, so that we don't have any strong separation. We only have separation a little bit on the back, and that's also people trying to diminish that by doing a better design. And it's not just aerodynamic. Of course, there are many factors that we have to take into account. If it was just aerodynamic, then the optimum shape is probably a flat plate for a car. But no, we need passengers and stuff to be in the car, so it needs to have a volume. Anyways, long story short, well, so with taking into account friction, viscosity, and no slip boundary condition, we should be able to get a non-zero, non-vanishing drag on a cylinder. But in order to get the actual analytical form, we need to solve Navier-Stokes equation, and we know that that's not easy to solve. So in fact, as of today, we don't have a solution to the Navier-Stokes equation for a circular cylinder in a general case. So what should we do? We have to go to the lab and start doing experiments. Well, what's the first step before doing the experiments? Dimensional analysis. Dimensional analysis. Always we have to do this first to basically first understand what are the parameters that are important in the problem, what kind of experiments we need to do. Well, okay, so let's quickly do that. We have a circular cylinder. We have a uniform flow, U. What are the parameters that are involved in this problem? Well, U is certainly important. We're looking for drag force on the cylinder. So this is important. We just said that viscosity, if you don't take viscosity into account, we get zero velocity. Viscosity is important. Well, the larger the cylinder, we expect the force, the drag force to be larger, so the diameter is important. And density of the fluid is also important, rho, right? I mean, if it's mercury or water versus air, of course, we expect a different resistance. So how many parameters we have here? N is 1, 2, 3, 4, 5. And let's make the dimension matrix quickly. So we have M, L, T, and then we have rho, D. It doesn't matter. I can just follow the same order. U, F, D, mu, D, and rho. All right. So let's go from here, which is easier. M is mass -3, 0. D is 0, 1, 0. Mu, I don't remember, so let's quickly calculate. Delta U, delta Y. Tau is F over A, so it's M LT -2 over L2. That's dimension of mu. U is L over T, and this is L. So L goes away with this L, and therefore we get dimension of mu is equal to M L -1 T -1. So M L -1 T -1. Force is mass times acceleration, M L T -2, and velocity is L T -1. Okay. So what's the rank of this matrix? Rank of this matrix is equal to, again, I'm going to be a little qualitative here. So this one has mass in it. It doesn't have mass in it. So these two are independent. And then if I have something that has time in it, like U, then these three are independent, because I mean, the time component here is 0 and 0. There's no way I can get U out of the rho and D. So therefore, well, we said that the rank is cannot be exceeding 3 because this is a 3 by 5 matrix. So the rank is 3. Therefore, the number of dimensionless groups that we're going to have is 5 minus 3 equal to 2. Okay. If you allow me to get rid of this here, that's going to make our little extra space. So therefore, we're going to have two dimensionless groups. The core variables I'm going to pick, core variables. Let's pick rho, U and D. We already know that they're independent linearly. Okay, so our pi 1, rho to the power alpha, U to the power beta, D to the power gamma times FD. Okay, so therefore, well, that's it. Yeah, that's pi 1. So therefore, from dimensional perspective, that's going to be M L -3 to the power alpha, L T -1 to the power beta, and L to the power gamma times M L T -2. That's the force. So that has to be 1. Powers of M is alpha plus 1 equal to 0. Powers of L, -3 alpha plus beta plus gamma plus 1 equal to 0. Powers of time, negative beta minus 2 equal to 0. So from here, we get alpha equal to -1. From here, we get beta equal to -2. And let's see from here what we get. So alpha is -1, so we get 3 minus 2 plus gamma plus 1 equal to 0. So we get gamma is equal to 0, right? Huh. Oh, no. Oh, yeah, 4. So that's 4 minus 2. No, it's not 0. 4 minus 2 is 2. So gamma is equal to -2. All right. So therefore, from here, we get that the pi 1 is rho to the power -1, U to the power beta, which is -2, D to the power -2 times FD, or pi 1 is equal to FD divided by rho U2 D2. Okay, so this is our first pi. Good. And then the second pi, we're going to do the same thing. Pi 2 is equal to rho to the power alpha, u to the power beta, d to the power gamma times mu. Same story. I can just even copy paste that thing, but it's okay. I can just write it down. You can just move forward on the video. -3 to the power 2 if you're comfortable. If not, you can definitely follow the steps. Power alpha, lt -1 to the power beta, L to the power gamma, and mu we already calculated. The dimension is m L -1 T -1. In fact, it's a good practice to be able to guess what kind of dimensionless number we're going to get here. We have mu, rho, u, d, so it's going to be Reynolds number, right? And if you don't believe me, I can do the calculation for you. So for m, we get alpha plus 1 equal to 0. For L, we get -3 alpha plus beta plus gamma minus 1 equal to 0. All right. And for time, we get negative beta minus 1 equal to 0. So alpha equal to -1. From here, we get beta equal to -1. And then from here, we get 3 minus 1 plus gamma minus 1 equal to 0. Therefore, gamma is equal to -1. So therefore, pi 2 is equal to rho -1, u -1, d -1 times mu, or pi 2 is equal to mu, so it's divided by rho u d. There you go. And this is 1 over Reynolds number. So based on Buckingham pi theorem, the solution to this problem is in this general form, f of pi 1 and pi 2 equal to 0. And usually we can express one as a function of the other. So we can express this as pi 1 is equal to another function of a single variable function of pi 2. All right. Or if I want to write it in an explicit form, so that's going to be fd divided by rho u2 d2 is equal to a function of mu over rho vd, or rho ud. That's good enough, but again, it's customary in the field that the first term is written as fd over 1/2 rho u2. I'll just put a constant here. It really doesn't matter. That's going to just change the value of this function. And instead of d2, d is a measure of the diameter of the object. So again, it's customary that people use the projected frontal area for the case of cylinder. So A is the projected frontal area for cylinder and many other blunt or bluff objects. So if it's a cylinder, right, in this direction, then nicer cylinder. So if this is a cylinder, then the projected frontal area is well, some d times L, right? So it becomes d times L, and sometimes, well, basically, if you want to have a 2D plot, we're going to plot force per unit length of the cylinder, and therefore we just put the d in denominator and we just say L is unity. So basically what is written is fd, and that's going to be per unit length of the cylinder divided by 1/2 rho u2 times d. All right. And then instead of f, I'm going to use a new function, and instead of Reynolds number, I'm going to use 1 over Reynolds number. So that's going to be, well, 1 over the pi 2. So that's going to be rho ud divided by mu, which is in fact now the Reynolds number. Now, the first term, this one, is called CD or drag coefficient. CD or drag coefficient. Drag coefficient. And so that's a function of Reynolds number. That's the general form of the solution. Now, I would like to comment briefly here that going from the force, the D2 to area, and then going to the per unit length case, there's an alternative, more rigorous way to do it. And basically, we could start from the beginning and say, hey, D is important and L is important. So therefore, the variables we're interested in turns into, what was that? UFD mu, diameter and density, so 5. And then if L is important, L becomes another parameter. So our number of variables now 6. The rank of the matrix is going to be 3, and therefore we're going to have 3 dimensionally independent group. One new group that we're going to have other than the 2 that we already have is L over D, or the aspect ratio, right? And therefore we still get FD over rho 2 U2 D2, and then so that is a function of the Reynolds number, or 1 over Reynolds number, and L over D. But again, from the experiments and experience, we know that we can basically combine this pi 1 and pi 3 in this way. So it gives an FD over rho U2 D2 times D over L, and that becomes FD over rho U2 DL, which is what we eventually have here. And if L is 1, or we want the force per unit length, then we just leave the D here. All right, so this is an alternative way. If you're not fully convinced by my explanation, we can go that route. Okay, so CD is just a function of Reynolds number. We're all set. All we need to go is to go to the laboratory, to the lab, and have a cylinder. The size doesn't matter, large or small. All we need to do is just vary either the size or the velocity or the viscosity or the density, such that the Reynolds number varies from a small value to large value. It doesn't need to be one experiment, and then measure the force. And basically what we need to report to the world is curve of CD as a function of Reynolds number. And if we have that, then the problem of fluid flow about a circular cylinder, at least experimentally, is now fully resolved. Well, the good news is this is a very important problem, and as a result, people have done all the experiments for us. This is just a few experiments out of a huge number of experiments that have been done on this problem. I give a reference here. I picked this from this paper. Again, it's just a very generic curve. You just search for drag on a circular cylinder and you get 5 million versions of the same thing. So we have Reynolds number on the x-axis and CD on the y-axis, and as you can see, the CD starts from very large value of 200, 300, 350 at 0.01, and it goes down and so on and so forth. So again, if a cylinder is given to you with its properties, all you need to do is just calculate the Reynolds number and move on. Let's work at a very simple problem, maybe quick example here. That's going to be helpful. Example, let's say we have a chimney with a diameter, say 2 meters. All right, so diameter is 2 meters. Air density, let's say, is 1. Viscosity of air is 10 to the negative 5. Wind is blowing at a speed of, say, 20 meters per second. All right. And the question is to calculate the force on this chimney, total force. And the height of the chimney is, say, 40 meters. Drag force. Well, you say the first step is, let's calculate the Reynolds number. So the Reynolds number is rho V D over mu. Rho is 1, V is 20, D is 2, mu is 10 to the negative 5. So that's going to be 40 10 to the 5, or 4 times 10 to the 6. We go here. We don't have 4 times 10 to the 6. It's okay. So we'll go with the best number that we have. So 1. So therefore, we get the Reynolds number of, we get the CD of 0.1, 0.2, 0.3. 0.3 is a good number. or 0.35. So CD is 0.35. Okay. Now CD is going to be equal to FD over 1/2 rho V squared times D. That's FD divided by 1/2 times 1 times 20 to the power 2 times 2. So therefore, FD is equal to, that's 400. This 2 and this 2 goes away. 400 times 0.35. Okay, and let me get the calculator. What is this? Forget about this. All right. So I have 400 times 0.35. There you go. So it gets us 140 Newton. 140 Newton. But pay attention that, remember, this is force per unit length. So this is, to be strict, this is 140 Newton per meter, right? And then if I want to calculate the F total, FD total, then that's going to be FD times the total length, which is, we said 40 meters. So that's going to be 140 times 40. That's for 16, that's going to be 56 and 2 zeros in front, right? Newton. So the total force on the chimney is going to be FD total is going to be 5,600 Newton of force. Okay. Now, so this is the drag, but then there is another interesting thing about the fluid flow, about the circular cylinder, and that's different qualitative regimes that we get for the flow field inside a circular cylinder. And again, there's been also observations. The plot that I'm showing you is from this 1966 report. Just maybe give credit here. All right. So basically, if Reynolds number is less than 5, very low Reynolds number, we get a nice flow going about the cylinder. Still, because of viscosity, we have friction. If Reynolds number is larger, below 40, between 5 to 40, then we have separation, and these vortices are formed on the downstream of the cylinder. Now, further increasing the Reynolds number to about 100, 140, 50, in this regime, then the vortices become unstable, and then the entire flow become unstable. So from here, we have instability. Remember, we have a uniform incident current, right? And in a linear system, we don't expect any frequency to be generated because of a linear motion, because of a non-uniform motion, right? Frequency in, same as frequency out. Zero frequency in, zero frequency out. But because our system is non-linear, from a uniform input, we're going to get instability and non-uniform, non-steady, it's uniform, but non-steady vortex shedding. And that's a term that we use, vortex shedding downstream. And this is called Kármán vortex street. That's another term, Kármán. Kármán was the first one who studied these carefully. Vortex street downstream of a cylinder. So this is really the first indication of really nonlinear behavior in the Navier-Stokes equation. So at that range of Reynolds number, we're going to have these vortex shedding. And you can imagine if you have a vortex shedding, there's going to be a periodic force acting on the cylinder, right? So if a cylinder is not rigid, all right, so if it's connected to springs or it has a lot of flexibility, so the cylinder is going to start to move up and down, all right? So then this is called vortex induced vibration, which is super important. That happens to chimneys, that happens to buildings, that happens to the risers in the oceans. And they're very important because even if the magnitude is not huge, because of the fatigue, right, that's gonna result in some really serious issues. Now, further increasing the Reynolds number, we're gonna have some turbulent behavior, that's another kind of instability, starts to appear in the vortices downstream. Further increase of the Reynolds number when we're talking about 10 to the power 5, right? Then the wake or whatever we have on the downstream of the cylinder is fully turbulent. We have a laminar boundary layer, as mentioned here. Laminar boundary layer has undergone turbulent transition. And then by further increasing the Reynolds number above 3.5 10 to the power 6, the vortex street and everything is very, very turbulent, as you can see from the picture. So there are really different regimes based on the Reynolds number. And these regimes are not obvious from this one. This talks about the average drag, but then we can see that we expect a different behavior downstream of the cylinder. So we can get these pictures and these numbers from either experiments or numerical simulations. And there are a lot of discussions about the vortex shedding. We also have a dimensionless number for that, and curves and plots, and how to basically do the calculation. In terms of application, as I said, huge number of applications. In fact, the discovery of Kármán vortex shedding was because of the Tacoma bridge failure. That was, people didn't know about this phenomenon, so the bridge was not designed for the vortex shedding, and it was not basically carefully designed against the vortex-induced vibration, and that result in the total failure of the bridge. In aerospace, in airplane design, we have the Flutter Effect, which is again an example of the so-called hydroelasticity. But probably here I'm going to stop. If time permits, later on I'm going to talk about some of the aspects here. So that's it for here. Let me quickly review what we did. So we said potential fluid theory doesn't work, so we have to take into account viscosity. We can't solve Navier-Stokes equation, so let's do dimensional analysis and go to the lab. We did dimensional analysis. We got two dimensionless groups. One we called drag coefficient, and the other is 1 over Reynolds number. So in the general form, we can write CD as a function of the Reynolds number. Let's go to the lab. People have gone already to the lab and did the test for us. There you go. This is the drag coefficient. That's more than enough to solve many of the problems in practical engineering, including the one that I gave you the example. And well, if you want to learn more about the behavior, let's just look at the flow field, the different regimes that we have. And these are the different regimes that we have in the problem of flow past a circular cylinder.